What I'd like to do now is talk a little bit about L'Hopital's rule. L'Hopital's rule is a very powerful technique that lets us evaluate limits of various types when we have a so-called indeterminate form. Roughly speaking, these are places where one of the standard rules doesn't apply because we're in some sort of an illegal domain situation. So, for example, let's suppose we're trying to calculate the limit of f of x over g of x. So we have two functions, f of x and g of x. We're trying to figure out the limit of the quotient. Now, what we know is that we can just say that this is the limit of one divided by the limit of the other if we are in the situation where the limit on the bottom doesn't go to 0. So we're going to pretend we're in this horrible situation where both the top and the bottom go to 0. This is called a so-called indeterminate form case. So here in the orange, we have this condition that both the limit for the top is 0 and the limit for the bottom is 0. So we would say in that case that this expression looks like 0 over 0. And in this situation, what L'Hopital's rule says is that we are allowed to get, we get the same answer by looking at this limit as looking at the limit where the functions are replaced by their derivatives. Similarly, the same rule applies if we have an infinity over infinity situation. So if f and g both go to infinity, then again, you get the same answer by taking derivatives at the top and the bottom. Okay, so let's get a feeling for this rule by looking at an example, and then I'll say a little bit about why such a rule might actually be true. Okay, so for example, let's look at the limit as x goes to 0 of the sine of 2x divided by x. Now at this point we have a number of ways for dealing with this limit, but let's just forget about all these things and take it from scratch. You know that if you directly try to plug in, you get that the sine of 0 on the top when you plug in 0 is 0, and x when you go to 0 is 0. And so this, the top goes to 0, the bottom goes to 0, which means we are in this particular situation. The top goes to 0, the bottom goes to 0. We would say this is an indeterminate form of the type 0 over 0. Because we have such an indeterminate form, L'Hopital's rule applies, and we know that we're going to get the same answer by taking the same limit, but by replacing the top with its derivative. So the derivative of sine gives me a cosine of 2x, and then I have to use the chain rule, multiply by the derivative of the inside. And taking the derivative of the bottom gives me just a 1. So these two limits are actually going to give me the same answer. But then the second one is very easy to evaluate. I can just plug in. Everything is nice and continuous. If you plug in, you get the cosine of 0, which is 1, times 2, divided by 1. The answer is 2. It's a very quick and easy way to do that limit. As another example, let's take a look at a limit going to infinity. So limit as x goes to infinity of 3x minus 2 divided by x plus 4. Now, in this case, if we were to just kind of plug in or take a limit or evaluate what happens to the top and the bottom separately, what we find is that the top gets very big, because you have 3 times big minus 2 is big. The bottom is big plus 4 is big. We have an infinity over infinity type situation, both the top and bottom go to infinity. And so this is also an indeterminate form of the type infinity over infinity. And again, this is one of our special situations where L'Hopital's rule applies. L'Hopital's rule says, in this case, as it always does when it applies, that I can replace the top by its derivative. The derivative of 3x minus 2 is 3, and the bottom, the derivative is 1. And so the limit is the same as the limit of 3 over 1, or in other words, just 3. And again, this is a very elegant, quick way of doing this problem. Okay. Occasionally, you might have to do L'Hopital's rule more than once. Just to give another example, let's suppose we have a similar situation, but now we have, I don't know, x squared minus 2x plus 1 over 3x squared plus 4. In this case, again, we can easily analyze that the top and bottom both go to infinity. We have an infinity over infinity type situation. And so that means that I can apply L'Hopital's rule and take the derivative of the top and the bottom. Taking the derivative of the top gives me a 2x minus 2. The 1 goes away. And the bottom I have a 6x. Okay, this is much simpler, but it's not done. The problem, of course, is that still we have an infinity over infinity situation. If we were just to look at the top and bottom individually, we see that they both get large. We have infinity over infinity, and therefore, infinity over infinity being one of our legal indeterminate forms, we can apply L'Hopital's rule again and say that that's the same as the limit of the derivative of the top, which is a 2, divided by the derivative of the bottom, which is 6, giving us an answer of 1/3. Which again was a relatively quick way of getting through this problem. All right, let's now just work out some examples using limits and L'Hopital's rule. How about we'll start with the limit as x goes to 0 of the cosine of x minus 1 divided by the sine of x. The first thing to do, of course, is to see what happens if we were to evaluate the top and the bottom separately. For the top, we see that as x goes to 0, we get cosine of 0 minus 1, which is 0. For the bottom, we get sine of 0, which is 0. And so this says we have an indeterminate form of the type 0 over 0. 0 over 0 means we can use L'Hopital's rule. And L'Hopital's rule says that provided the answer we get, provided we get a good limit over here, then this will be equal to the limit of the derivative of the top divided by the limit of the derivative of the bottom. And the derivative of the top, the derivative of cosine is minus sine. The minus 1 doesn't do anything. The derivative of the bottom is a cosine. And there we are. And now we start again and we say, what happens when we try to evaluate this? So in this expression, the top is going to go to the minus sine of 0, which is 0, and the bottom to the cosine of 0, which is 1. Now we're in good shape. The top is 0, the bottom is 1. That is a legitimate answer, and the answer is 0. L'Hopital's rule is an extremely subtle, powerful, interesting rule, and we really shouldn't take it for granted. Why should it be the case that you're allowed to take the derivative of the top and the bottom and still get the same answer in this limit? It's kind of a miracle that this stuff works. Just so that we have some feeling of being grounded in this, let me talk through at least why it's not unreasonable that this might work in one of these types of cases. So let's pretend we have two functions, as usual, f of x and g of x. We'll suppose that if you were to just plug in some value a in both of them, you would get 0. And let's suppose we're trying, they're continuous functions, let's say. And let's suppose we're trying to evaluate this limit of f of x over g of x. And how would we want to proceed? The idea is I'm going to try to relate this to the derivatives, and therefore to these difference quotients. So remember, these are things that look something like, f of a plus h minus f of a over h, and the limit as h goes to 0, etc., things like that. This is, by definition, the derivative of f at the value a. We would like to go from these expressions to difference quotient derivative type expressions. So the first thing that we're going to do is we're going to say, well, what does it mean for x to get close to a? If x is getting close to a, then one way to say that is I could let h be the difference between x and a. So I could let it be x minus a. And to say that x is getting close to a is really like saying h is going to 0. So I could say I want h to go to 0. Of course, to say h is x minus a is the same as saying x is h plus a. And now I'm looking at, or a plus h, maybe sounds a little better. So I'm looking at the limit of f of a plus h divided by g of a plus h. And I'm letting h get small so that the top and bottom are getting close to f of a and g of a, which was the original limit that I wanted to try to evaluate. This is a little bit better because I have this chunk of my difference quotient, but let me modify it by subtracting off the other chunk. And now the observation is that that modification is for free because, well, what is f of a? By assumption it's 0, and g of a is 0. So when I make this following modification here, subtract off f of a, I actually haven't done anything at all. F of a is 0 and g of a is 0. These are really just the same expressions, but of course they look more like the difference quotient, and that's going to help us pattern match things as we move. Now, to make this look a little bit more like the difference quotient, I want to have this thing divided by h instead of that. So I'm going to stick in an h over h. Because that doesn't do anything, and it'll provide me with the h's I need to rewrite my expression. So you get the limit as h goes to 0. And now let me pair these off, kind of in different ways. So on the one hand, we have f of a plus h minus f of a over h. And on the other hand, we have an h divided by g of a plus h minus g of a. So I've just taken this expression over here, and I've grouped my terms like this and like that to make these two terms. Now, give myself a little bit of room. I want to rewrite this as a fraction where this is the top and this is the bottom. To stick this in the bottom, I need to flip it. So I have this big kind of compound fraction here. F of a plus h minus f of a over h. That's on the top. And the bottom, I have g of a plus h minus g of a over h. And now, if I'm lucky, my limit laws will let me break this up as the limit of the top and the limit of the bottom. So I get the limit of f of a plus h minus f of a over h. H goes to 0, divided by the limit as h goes to 0 of g of a plus h minus g of a over h. But what are these things? This top is by definition the derivative, and the bottom is the derivative of g. So this is f prime of a over g prime of a. So in other words, if you can take the derivative and just plug in, you get the same answer as your original limit. Okay? So this is some motivation for why L'Hopital's rule would work. This is kind of if it works in one step, and then you have to make a slightly more subtle argument to make this exactly line up with the way we've stated L'Hopital's rule. And of course, we haven't considered infinity. We've just considered if you have a 0 over 0, not an infinity over infinity. But this is the rough idea of kind of plausibility of how the limit of f over g should ever relate to f prime over g prime.